Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematical science. In this session, we are going to discuss about solving of a given integer programming problem by making use of branch and bound method. So, in the previous session, we discussed about this problem maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, x1 x2 greater than or equal to 0 and an integer. And we obtain the optimal solution for this problem as maximum z equal to 32 by 7 with the values of x1 equal to 4 by 7 and x2 equal to 12 by 7. So, for the given problem, the optimum value is x1 equal to 4 by 7 and x2 equal to 12 by 7, but this optimum value is not an integer because the restriction on x1 and x2 should be an integer. Here both are non-integer. So, in order to obtain the integer optimal solution, we have to partition the given problem into 2 sub problem. For that, first I will consider x1. x1 is 4 by 7. The fractional part of this one is 0 plus 4 by 7. Now, we take x2. x2 is 12 by 7. The fractional part of this one is 1 plus 5 by 7. Now, among these two, among this x1 and x2, the maximum fractional part is 5 by 7, which corresponds to x2. So, here the maximum fractional part occurs for x2 and x2 satisfies the condition x2 less than 2 and greater than 1. So, from this x2 satisfies the condition x2 less than 2 and greater than 2. Now, the feasible integer solution of x2 satisfies the condition x2 less than or equal to 1 or x2 greater than or equal to 2. So, from this inequality, the feasible integer solution of x2 either satisfies the condition x2 less than or equal to 1 or x2 greater than or equal to 1. Now, these two conditions leads to the original problem into various sub problem. So, our sub problem 1 is original problem with this restriction and our sub problem 2 is the original problem with this restriction. So, in order to obtain the integer optimal solution, we have to branch the original problem into 2 sub problem. Now, with the help of these 2 restriction, we have 2 sub problems. Therefore, our sub problem 1 is maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8 and x1 plus 2x2 less than or equal to 4 and the second one condition is x2 less than or equal to 1, x1 x2 greater than or equal to 0. So, by adding this extra constraint to the original problem leads to this sub problem. Now, in order to get the optimal integer solution, now we have to solve this sub problem. This sub problem 1 involves 2 decision variable x1 and x2. So, in order to obtain the optimal solution, we can make use of either simplex algorithm or graphical method. Since it involves only 2 decision variable, with the help of graphical method, we try to obtain the optimal solution for this problem. So, in order to obtain optimal solution for this problem in a graphical method, First we should consider, by temporarily ignoring the inequality sign of these two constraints, first we should consider the equation 5x1 plus 3x2 equal to 8 and x1 plus 2x2 equal to 4. Now by plotting these two curves in this equation in the graph, we will get the feasible region. From the feasible region we can get the optimal solution. First idea is we have to plot the given constraints in the graph. The first curve is 5x1 plus 3x2 equal to 8. So this curve is obtained by joining the points 8 by 5 comma 0 with 0 comma 8 by 3. So now by joining these two points we get the curve 5x1 plus 3x2 equal to 8. Now the next curve is x1 plus 2x2 equal to 4. This curve is obtained by joining the points 4 comma 0 with 0 comma 2. So now by joining these two points we will get the curve x1 plus 2x2 equal to 4. So this is our curve x1 plus 2x2 equal to 4. Now the third constraint is x2 less than or equal to 1. So consider the curve x2 equal to 1. Now the curve x2 equal to 1 is the curve passing through the point 1 and parallel to x axis. So this is our curve x2 equal to 1. So now the given set of constraint is 5x1 plus 3x2 less than or equal to 8. Therefore our feasible region as far as the curve 5x1 plus 3x2 concern is below this one. And for the second constraint is x1 plus 2x2 less than or equal to 4, the feasible region is below this one. And for the curve x2 equal to 1, the feasible region x2 less than or equal to 1 means this one. Now the common region which satisfies these three constraints is the region in between O to A and A to B and B to C. So our feasible region is the region bounded by the vertices O, A, B, C. So this is our feasible region. Now for our problem, the optimum value occurs only in the feasible region. In particular, our optimum value occurs either at O or at A or at B or at C. Now our point O has the coordinates 0, 0 and our point A has the coordinates 8 by 5 comma 0 and our point C has the coordinates 0 comma 1. Now we are interested in finding the coordinates value of B, but B is the point of intersection of the curve x2 equal to 1 and 5x1 plus 3x2 equal to 8. So now by solving the equation x2 equal to 1 and 5x1 plus 3x2 equal to 8, we will get the value of x1, x2, which is the coordinates value of the B. By solving these two equations, we will get our x1 as 1 and x2 equal to 1. Therefore, the coordinates B are 1 comma 1. So coordinates of 0 is 0, 0 and A is 8 by 5 comma 0 and coordinates value of B is 1, 1 and C is 0 comma 1. Now the maximum value of the objective function occurs either at 0 or at A or at C or at B. Now the maximum value, which is 2x1 plus 2x2, for the coordinate 0 is 0 and for 8 by 5 is 2 into 8 by 5 plus 2 into 0, which is 16 by 5, and for C is 2 into 0 plus 1 2 into 1, which is 2, and for B is 2 into 1 into 2 into 1 4. So out of this 4 value, the maximum value occurs is 4, which corresponds to the coordinates B, which takes the value 1, 1. Therefore, the optimum value for the given problem occurs at the point x1 equal to 1 and x2 equal to 1. With this x1 and x2, our maximum z equal to 2x1 plus 2x2 gives us 4 value. So, the optimal solution of the sub problem 1 is maximum z equal to 4 with the value of x1 equal to 1 and x2 equal to 1. Here the optimal solution takes an integer value. Therefore, optimum integer solution for the sub problem 1 is obtained. Therefore, further branching of sub problem 1 is not needed. So, since the optimal integer solution occurs for sub problem 1, the sub problem 1 does not need any further branching. Now, we will consider the sub problem 2. Our sub problem 2 is maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, and our constraint is x2 greater than or equal to 2, x1 x2 greater than or equal to 0. Now, by adding this constraint x2 greater than or equal to the original problem, we got our sub problem 2. So, our sub problem 2 is maximum z equal to 2x1 plus 2x2 subject to the constraint 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, x2 greater than or equal to 2. Now, we are interested in finding the optimal integer solution for this sub problem. Now, in order to get the optimal solution, we have to find out the solution of this sub problem either using graphical method or simplex algorithm. Since this sub problem 2 involves 2 decision variable, we try to solve this problem by the method of graphical. So, our sub problem 2 involving 3 set of constraints. The first constraint is 5x1 plus 2x2 less than or equal to 8, second constraint is x1 plus 2x2 less than or equal to 4, and the third constraint is x2 greater than or equal to 2. Let us have a break. Welcome back. Before break, we solve sub problem 1 using graphical method. Now, our sub problem 2 consisting of 3 constraints. First, we try to draw the first constraints 5x1 plus 3x2 equal to 8 in the graph. Curve 5x1 plus 3x2 equal to 8 can be obtained by joining the points 8 by 5 comma 0 with 0 8 by 3. So, by joining these 2 points, we got the curve 5x1 plus 3x2 equal to 8. Our next constraint is x1 plus 2x2 equal to 4. This curve is obtained by joining the points 4 comma 0 with 0 comma 2. So, by joining the points 0 2 with 4 0, get the curve x1 plus 2x2 equal to 4. In the sub problem 2, the third constraint is x2 greater than or equal to 2. Now, we have to plot this curve in the graph by temporarily ignoring the inequality sign. This inequality becomes x2 equal to 2. Now, x2 equal to 2 is the curve passing through the points 2 which is parallel to x axis. So, this is our curve x2 equal to 2. Now, our feasible region is the region common which satisfies these 3 set of constraints. The first constraint is 5x1 plus 3x2 less than or equal to 8. Therefore, our area should be towards the origin below this curve. Next, the second constraint is x1 plus 2x2 less than or equal to 4. So, therefore, the corresponding area is towards the origin below this area. The third constraint is x2 greater than or equal to 2. Therefore, our area is away from the origin. So, our area is above this line. So, the first constraint, as far as the first constraint 5x1 plus 3x2 less than concerned, the area is below this line. For the curve x1 plus 2x2 less than or equal 4, the area is below this line. For the constraint x2 greater than or equal to, now the area is away from the origin. Now, our aim is to obtain the feasible region which satisfies these three constraints. Now, the feasible region common to this area consisting only one points, the points 0, 2. So, the feasible region which satisfies these three constraints consisting only one points, that is 0, 2. So, since our feasible region consisting only one points, for the subproblem 2 maximum occurs only at this point 0, 2. Therefore, for the subproblem 2, the solution, optimal solution is x1 equal to 0 and x2 equal to 2 with the maximum z equal to 4. Therefore, for the subproblem 2, the optimal solution is x1 equal to 0, x2 equal to 2 with maximum z equal to 4. For the subproblem 2, the optimal solution is an integer solution, x1 takes 0, x2 takes 2, both are integer. Since the optimal solutions involve integer solution, further branching of subproblem 2 is not needed. Therefore, so for the subproblem 1, we will get the optimal solution as an integer solution, and the subproblem 2 also we got optimal integer solution. Therefore, we can stop the process. Therefore, for subproblem 1 and 2, we doesn't need any branching. So, the optimal solution for this problem is x1 equal to 1 and x2 equal to 1, or x1 equal to 0 and x2 equal to 2 with maximum z equal to 4. So, the optimal solution to the given integer programming problem is x1 equal to 1 and x2 equal to 1, or x1 equal to 0 and x2 equal to 2 with maximum z equal to 4. So, the given original problem is maximum z equal to 2x1 plus 2x2 subject to the constraints 5x1 plus 3x2 less than or equal to 8 and x1 plus 2x2 less than or equal to 4, x1 x2 greater than or equal to 0 and integers. This is our original problem. Now, for this original problem, our optimal solution is x1 equal to 4 by 7 and x2 equal to 12 by 7 with maximum z equal to 32 by 7. So, our original problem is this one. For this problem, by making use of graphical method, we obtain the optimal solution as x1 equal to 4 by 7 and x2 equal to 12 by 7 and maximum z equal to 32 by 7. Here the restriction on x1 and x2 are integer, but here our x1 and x2 are non-integer. In order to obtain the integer optimal solution, now we have to make use of branching method, and we have to branch this original problem into two subproblems. In order to obtain two subproblems, we should look into the value of x1 and x2. Among this x1 and x2, x1, the fractional part of x1 is 0 plus 4 by 7 and the fractional part of x2 is 1 plus 5 by 7. From this, the maximum fractional part is 5 by 7, which corresponds to x2. Therefore, x2 satisfies the condition x2 less than 2 and greater than 1. Now, a feasible integer solution of x2 satisfies the condition x2 less than or equal to 1 or x2 greater than or equal to 2. So, the any feasible integer solution of x2 satisfy either x2 less than or equal to 1 or x2 greater than or equal to 2. Now, with the help of these two conditions, we branch the original problem into two subproblems. So, this problem by this condition becomes two sub problem. Our sub problem 1 is maximum z equal to 2x1 plus 2x2 with condition 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4 and x2 less than or equal to 1. This is our sub problem 1, and our sub problem 2 is maximum z equal to 2x1 plus 2x2 subject to the condition 5x1 plus 3x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4 and the condition is x2 greater than or equal to 2. So, this constraints branch the original problem into two sub problem. This is our sub problem 1 and this is our sub problem 2. Now, by solving this sub problem either by making use of simplex or graphical method, we will get the optimal solution. If our optimal solution involves an integer solution, this sub problem branching is stopped. Otherwise, again we have to branch this sub problem into 2. As far as this sub problem concerned, we obtain the optimal solution as x1 equal to 1 and x2 equal to 1. Therefore, this sub problem has two integer solution as an optimal solution. Therefore, no need to branch this sub problem into another sub problem. Now, for the sub problem 2, we obtain our optimal solution as x1 equal to 0 and x2 equal to 2. Here also our optimal solution involves integer solution only. Therefore, further branching of this sub problem is not required. Therefore, we have to stop the process. Therefore, the given original problem has optimal solution as maximum z equal to 4 with either x1 equal to 1 and x2 equal to 1 or x1 equal to 0 and x2 equal to 2. So, let me recap of branch and bound methods. The first step is, first we have to solve the given integer programming problem by considering as a continuous linear programming problem by temporarily ignoring the inequality signs. So, first by considering the given IPP as a LPP, by applying simplex method we have to solve the given LPP. Once we obtain the solution, if the solution involves non-integer solution, then the next idea is we have to partition or branch the original problem into sub problem and we have to solve the sub problem. At least one of the sub problem gives an integer optimal solution, then for such a sub problem further branching is not required. But if any sub problem does not give integer optimal solution, then again that sub problem branched into two sub problem. This branching process is continued until each problem terminates with optimal integer solution or there is an indication that it cannot give the best optimal solutions. Now, the optimal solution to the original problem is the integer valued solution among all sub problem which gives the most optimum value of the objective function. The problem is solve the integer programming problem using branch and bound method, maximize z equal to 3x1 plus 4x2 subject to the constraint 3x1 plus 2x2 less than or equal to 8 and x1 plus 4x2 less than or equal to 10 and x1 x2 greater than or equal to 0 and x1 x2 are integer. The given problem is a all integer programming problem which involve two decision variables. We try to obtain the optimal solution for this problem with the help of simplex method or graphical method. Once we get the optimal solution to the problem, we look into the integer optimal solution. If the optimal solution does not have an integer solution, then this original problem should be splitted into two sub problems. subproblem 1 and subproblem 2. Now, by solving this subproblem, we will get the solution to the original problem. While solving this subproblem, if any subproblem has integer optimal solution, then further branching of that subproblem is not required. But if any subproblem does not have a integer optimal solution, then that subproblem again splitted into the two subproblem, subproblem 3 and subproblem 4, and continuing this process we will get the optimal solution to the original problem. Thank you.